C2V point group is particularly simple because it consists of only one-dimensional irreducible representations. That is, representations that consist of a single number rather than a 2x2 or a 3x3 matrix. All right, I want to contrast this now with a different sort of point group so that we can see what that looks like. So to do this, I'm going to look at the C3V point group. Now, the symmetry elements for C3V consist of the following. We have a C3 axis of rotation, and I'm going to label that as the Z-axis for our purposes. And there are two possible symmetry operations that can be generated from that symmetry element. There are a simple rotation, a third of the way around, and two rotations, a third of the way around. So I'll call those C3 raised to the 1 and C3 raised to the 2. All right, we also have three sigma planes. So I have sigma V prime, sigma V prime prime planes of reflection. And of course, they generate three reflection operations, which I'll give simply the same labels: sigma V prime, and sigma V prime prime. All right, now, since these are generated, if you will, with respect to the C3 rotation axis, all three of these planes contain the Z-axis. So they're all, if I look at this picture over to the side, they're all going to be planes that are perpendicular to the page. One of them will lie along this x-axis, so we'll call that one sigma V. One of them will lie along this axis and the Z-axis. I shouldn't say it's lying along the axis, it's containing the axis. This one we'll call sigma V prime, and the third one will be the one that contains this axis. So I'll call it sigma V prime prime. So these will be my three planes, if you'll allow me to, the generalization of calling these dashed lines basically where the perpendicular planes hit the xy plane. And what I'm going to want to do is look at the effect that those operations have on different objects so that we can generate their irreducible representations. All right, let's start by looking simply at a vector along the z-axis. I'll call this u sub z, and we're going to be interested in how this transforms under all of these various operations. So I'll have C3 squared, sigma V prime, and sigma V prime prime. Okay, u sub z is not going to be changed at all by the identity operator, so that will give us 1. It will not be changed at all by rotation about it, because remember, C3 rotation is a rotation about the z-axis, so that will leave us 1, or 2 rotations. And since the z-axis is in all three of these reflection planes, none of them will affect this vector in the z direction. So in effect, what happens is this generates the totally symmetric irreducible representation for this point group. All right. Now, what if we looked at, remember we looked at a rotation operator for C2V. What if we looked at a rotation about the z-axis? Okay, so we're looking at, for example, perhaps a vector pointing in this direction, a vector pointing in this direction together, and how those are affected by these various symmetry operations. Well, a rotation about that z-axis is again not going to be affected by the identity operation or by rotations around that z-axis. And it turns out that each of these planes will have the effect of negating this rotation. If I think of this just as a loop with a particular sense of rotation, each of the planes will reverse that sense of rotation. So all of these three will have the effect of anti-symmetrizing the rotation. All right, so this leads to a different irreducible representation. But in both of these cases, I still have a one-dimensional irreducible representation. What would happen if I now look at something that is along the x direction? Well, I think it's pretty easy to see that if I start with a vector that's pointed in the x direction, after one rotation, I'm now going to have a vector that includes both x and y components. And in fact, since that rotation, and I should indicate the angle, the rotation is about an angle of 2 pi over 3. The place where I end up here, if I start at a vector that is 1, 0, the place I end up here will be a vector that has coordinates cosine of 2 pi over 3, sine of 2 pi over 3. And in effect what happens is I'll end up having this effect. C3 operating on 1, 0 is going to give me square root of 3, negative 1/2 square root of 3 over 2 as a result. So in effect it has mixed together the x and the y. A second rotation about this same point will generate negative 1/2 and negative square root of 3 over 2. And there's no way that I can separate x and y. So I have x and y are always mixed. And by mixed I mean if I start with a vector pointed along one of the axes, I will without fail get a vector that includes components in both of those two directions. So there's no way that I can separate them geometrically using a symmetry operation of this type. And that's the sense in which we link these together, and it causes their irreducible representation that they generate to be greater than one-dimensional. And in fact, if I were to construct the little 2x2 matrices that would generate these various operations, they would look like this. For the E operation, I would have a matrix that looks like this. For C3, I've already begun to indicate what that is. I'll have negative 1/2, negative square root of 3 over 2, negative square root of 3 over 2, positive square root of 3 over 2, minus 1/2. All right, for C3 working twice, I will end up with the following transformation matrix. I'll have minus 1/2, minus 1/2, and then I'll have negative square root of 3 over 2 down here and square root of 3 over 2 up here. For the sigma v operations, okay, this is the reflection about the x-axis that I can generate using this if I'm using u sub x as my basis vector. For the sigma v prime, it turns out that it will turn into this. We'll have minus 1/2, we'll have plus 1/2 along the diagonal, and square root of 3 over 2 in the two off-diagonal elements. For sigma v prime prime, again, I'll have minus 1/2 and plus 1/2 along the diagonal, but switched places, and minus square root of 3 over 2 and minus square root of 3 over 2 here. Now, I haven't gone through a detailed derivation of these matrix forms. I hope you will simply trust and have confidence that I've done this right, but I'll invite you to indicate what is the result of this matrix operating on a vector of 1, 0. So operate each of these matrices on this vector, and it should show you what the effect of these different symmetry operations would be on a vector that starts pointing in the x direction. Now, this, because x and y are inextricably linked, this represents a two-dimensional irreducible representation. I cannot do this with less than 2 dimensions. I can never separate x and y since the C3 rotation is about the z-axis. They will always be linked. All right, so how do we deal with this in terms of a way of systematizing our use of this? Do we have to always give 2x2 matrices? Well, it turns out there is one thing that becomes invariant with these matrices. I have chosen to start with u sub x as my generator here, but I could have equally well have started with uy as my generator of these. And that would have generated a different set of 2x2 matrices for these symmetry operations. So is there any way that I can generate or realize a similarity between those two representations? Well, in fact, there is, because these would simply represent the relationship between ux and uy as a rotation about 90 degrees, right? To go from ux to uy, I would just make a rotation of 90 degrees. So I could change all of these matrices by performing a coordinate transformation that rotates them by 90 degrees and get a different set of matrices. The thing that doesn't change, though, is the sum of the diagonal elements. All right, so the sum of these two diagonal elements in each case would remain the same no matter how much I rotated this. So the sum of those diagonal elements for each of these is, in the case of E, it's 2. In the case of C3, it's -1. In the case of C3 squared, it's -1. And then for each of the sigma V's, it's going to be 0. So here we have a consistent set of numbers, and these are the numbers that we use to represent the characters when we have a higher dimensional point group or higher dimensional irreducible representation. Right now, I want to stress that the dimensionality of these representations up here, UZ and RZ, the dimensionality of these is equal to 1. The dimensionality of this one, though, is equal to 2. And let's see what this looks like when we pull it together in a character table, and I've done this on the next page. So here is a character table that represents all of this, so we can see it laid out. So this was the first one that was generated by our operations on the UZ. This is the second one that was generated by our operations on RZ. And this is the third one that was generated by our operations on UX and UY. Okay, so I'm going to put parentheses around them to indicate that they have to go together. They can't stand separately, if you will. They're always mixed. And we can ascribe the different dimensions to this. The dimension of the first one is 1, the dimension of the second one is 1, and the dimension of the third irreducible representation is 2. Notice that that's the number that appears here. And that's, generally speaking, always going to be true. For the identity operator, the character that's listed in one of these character tables is going to be the dimensionality of that irreducible representation. So you can immediately tell what dimensionality the irreducible representation is going to have. Now, there's another particular relationship that is useful to know, and that is that the sum over all of the irreducible representations, so this is a sum over irreducible representations, IRR reps, of the dimensionality squared is always going to be equal to the order of the group. So in other words, remember the order of the group is the number of symmetry operations. H is equal to 6 in this case. Well, what we have for this particular point group in this particular character table is I've got 2 irreducible representations that have dimension 1, and I have one that has dimension 2. So I'm squaring all of these, and indeed 1 plus 1 plus 4 is equal to 6 as advertised. This will always be true for these point groups, and it's something that you can check in these character tables. Now, another thing that is useful to see here is that there are 3 irreducible representations, and that, and turns out, is equal to the number of classes. So we have 3 classes. Okay, those 3 classes are the identity operator, the C3 and C3 squared operators, and the 3 sigma V operators. These represent the 3 classes that the C3V point group has. So this predicts that number of classes is going to be equal to the number of irreducible representations. Now, the reason I draw your attention to all of these things is that once you've figured out what symmetry operations belong to a certain point group, and you can associate those symmetry operations in classes, as we're doing here, that immediately tells you how many irreducible representations you should have. And knowing that the order of the symmetry group, of the point group, has to be the sum of the squares of the dimensionality of the representations, however many there may be, gives you a big clue as to how what dimensionalities you would have. So if I knew that I only have 3 irreducible representations and that the sums of their squares has to add up to 6, it turns out this is the only way that could happen, if 2 of them were one-dimensional and 1 of them was 2-dimensional. We'll look more at the properties and what you can interpret from a character table in another video.